Hi, I'm going to talk about the physics of baseball lecture that I attended a few weeks ago. It was actually really interesting. It talked about the dynamics of the ball-bat collision, what makes for a better hit, the amount of components that go into what makes a ball go where it does, and how far it goes and how fast it leaves the bat and things like that. It's very interesting to see how there's so much physics that goes in just like such a tiny little time span of this collision between the ball and the bat. And the time span is actually very important in this dynamic because it's such a large force throughout such a small span of time, and that's what causes the ball to feel the force it does and go as far as it does and as fast as it does off of the bat. Because you've got a huge force from the bat, a lot of momentum coming from the bat, a lot of momentum coming from the ball, and when they meet, we learned in Physics 1 that they feel the same force, but there's a lot more mass behind the bat and the batter holding the bat than the ball, so the ball is going to feel much greater acceleration in the opposite direction that it was thrown, and that is what's going to create the ball or make the ball go towards the fence or whatever, where you want it to go. So the lecture mainly talked about this weird dynamic between the ball and the bat and like all the many components that go into that, and then he also talked a little bit about the trajectory of the ball after it's left the bat, and some aerodynamics behind what makes the ball slice off to the side or curve, and things like that. But first I'm going to start with the dynamics between the collision. So like I said, it's like a huge force between in such a small amount of time that creates that acceleration in the other direction. And it actually turns out that the speed of the bat is way more important than the speed of the ball. And there's actually an equation that I'll talk about in a second that shows that mathematically. And you can actually calculate the batted ball speed, or the speed that the ball leaves the bat, using a coefficient called Q, which is the collision efficiency. And this Q depends on a couple of things. It depends on the weight of the bat, and then also something called the coefficient of restitution. And we'll get to that in a second, but basically this Q plays a huge role in determining how fast the ball leaves the bat. There's actually an equation to determine the speed that the ball leaves the bat, and that is Q times the speed of the pitch plus 1 plus Q times the speed of the bat. So you can see just right there that the speed of the bat is way more important than the speed of the pitch. That 1 plus Q adds a ton of speed. It's a huge component of that equation. So if you're trying to hit the ball as far as you can, it doesn't matter so much how fast the ball is being thrown at you. It matters more how fast you're swinging the ball or swinging the bat at the ball. And this little Q, the collision efficiency, like I said, is dependent on the weight of the bat and then also this coefficient of restitution. And coefficient of restitution is just a fancy word for, I guess, the springiness or the bounciness of the ball and the bat. And you can think of it as like a trampoline. The higher the coefficient of restitution or this bounciness, the farther the ball is going to go, because if you were jumping on a trampoline versus jumping on a concrete floor, if you're jumping on the floor, you jump up, you land, you don't really feel yourself bounce up again. But if you just jump on a trampoline and just let yourself fall, collide with the trampoline, you compress the springs in the trampoline and it kind of bounces you back up. And that's the same thing that's happening with the ball. It compresses against the bat when it collides. The bat compresses a little bit, not as much, and then it kind of just springs itself off the bat in the other direction with a much greater velocity than if it were extreme, just straight, not bouncy at all. It wouldn't really go as far. And he actually compared that to tennis as well. He talked about if you're trying to improve your serve or make your serve go faster in tennis, you loosen the strings in your racket so that there's more compression when the ball collides with the strings, and then it just kind of springs it off in the other direction. So that's basically what the coefficient of restitution is, and plays a huge role in determining how fast the ball will leave the bat. There's also a few nodes along the length of the bat that also play a huge role in how hard you can hit it, or having a good hit, a solid hit as he called it. Those are called sweet spots, and the sweet spots are the places on the bat where there's the least amount of vibration when the ball hits the bat. He showed a few videos of a batter hitting the ball on a sweet spot versus somewhere a little closer to the handle, and when he hit it closer to the handle when it wasn't the sweet spot, the bat just vibrated, crazily, and then in some cases it would even break the bat, and that is detrimental to a good hit. And so if you hit on this sweet spot, there's very little vibration of the bat. You get a solid, clean hit, and the ball will travel off in the other direction at a much greater velocity, and will end up going a further distance. And so another thing that he talked about was aluminum versus wooden bats, and why aluminum bats are much better than wooden bats, or you get cleaner and better hits off of an aluminum bat because of this coefficient of restitution that I mentioned. With a hollow aluminum bat, the bat compresses more than a solid wooden bat would, so you get more of a springiness off of the bat, like I mentioned earlier, or a trampoline effect as he called it, and the ball ends up going further. So yeah.